Today we're going to be talking about friction stir welding. I'm Greg. Dane and Josh will be talking about some stuff a little bit later. But the friction stir welding process is the problem we were asked to look into. And we studied how to optimize the process by heating the stir rod prior to plunging so that the weld is of higher quality and it also reduces the startup time. The problem we were asked to try to find a solution to was if we could heat the top of the rod and within 2 minutes have the bottom of the rod that will be plunged be at a temperature of 400 degrees C. We used a low carbon steel rod and it melted around 1500 degrees Celsius, but it also lost temperature as we were heating it on the bottom of the rod due to convection and radiation. And in order to check to see if this is even possible, we did a feasibility study and we started heating the rod at 1450, so full bore. 295 seconds later, the bottom of the rod reached the 400 degrees Celsius point. But we also found that we had dead time in our process because in 2 minutes of heating, the bottom of the rod was still room temperature, and so the dead time was longer than 2 minutes, and we had to work with that.
So as far as our best possible case, first we fit our model. There was a little bit of confusion there. Our first thought was to use a partial differential equation to solve the energy balance explicitly, but that was kind of messy. We thought about doing a finite element analysis where the rod was divided into several nodes from the base to the tip, but we also abandoned that idea and ended up using Dr. Hedengren's partial differential equation model and actually approximated that model with a first order plus dead time model. In this case, it worked out really great. We had an R-squared value of almost 1, which for all practical purposes is awesome. Our input parameter we chose to use was top temperature rather than heat in. So our set points in the following tests will reflect that. We also conducted a doublet test around 1000 degrees to make sure that our process was linear and the constants were found to be the same. As Greg talked about, there is a significant amount of dead time with this process. We have a dead time of about 2 minutes here. We ended up using a Smith predictor to deal with this dead time, and what the Smith predictor does essentially is it prevents overshoot by dampening your controller output before you've reached your set point in an appropriate fashion.
Alright, so here was the setup of our Simulink model. At the top we have our actual process with our time delay, and then this lower loop down here, that's our Smith predictor. And when we ran it through with our original IMC correlations, we didn't get good results. So we got some fluctuation. This green one here, that's our tip temperature. And then also we have our PID output. We see the Smith predictor just plunged that to 0 almost right away. And then it popped back up, and we didn't really like that, so we played with our Smith predictor settings a little bit, changed our parameters, and changed our dead time, and we found some pretty optimal settings. We also had to change the PID controller, set the saturation points, number one, to keep it from going over the melting point, and then also to keep the lower saturation point up higher so we wouldn't plunge to 0 and get that fluctuation. So this here is this here is our optimum fit. You can see that the two transfer functions from our Smith predictor are right in line with each other, just enough to offset and give us a bump here on our PID output. It gets us to our set point as quickly as possible and with very little overshoot. This here is a zoom in of our output. This is the tip temperature with a step of 380 degrees, assuming 20 degrees ambient temperatures. And then this here shows our Smith predictor really kicking in right at the end. We have only 3 degrees of overshoot, and we reach within 1% of our set point within 6 minutes. So we felt that that was pretty optimal. We couldn't find anything better.